All right. So with probability, the main definition we're going to talk about with probability, and then I'm going to show you kind of an alternate way to think about it, which you're going to need, is the probability is defined as the number of ways that an event could occur over the total number of ways that occur in the sample space. And remember, the event would be like if I was drawing 5 cards from a deck of cards, that would be the experiment. And the number of ways that could actually happen would be the number of ways in my sample space. That's like all the ways to be successful or fail in this particular example. But the event would be what I'm trying to find the probability of occurring. Like the number, if I'm trying to get a full house, which if you don't know cards, that's like getting 3 of a kind and 2 of a kind. That makes a full house, which is very good hand. But if I calculate the number of ways for that to happen, if I take the number of ways that that particular event could occur, divide it by the total number of ways I can just draw any 5 cards, that would give me the percent chance or the probability that that occurs. And most of the time you write probability as a decimal or a fraction between 0 and 1. Is everybody with me? I sent some like people looking at stones in the wall, bricks. Normally we would say probability is between 0 and 1. Like I might say, yeah, there's a 0.7 probability that something would occur. But a lot of people say there's a 70% chance that it would occur, or the probability is 70%. That's kind of allowed because 70%, what does the percent mean? Divide by 100, and when you do that, it moves the decimal and creates a value between 0 and 1. But most people divide probability as between 0 and 1, 0 being an impossible event, 1 being a certain event, and then everything in between being where most of the situations lie. Are y'all with me? Okay, now there are times when I calculate probability that I can't look at the number of total ways something could occur as easily. And what I'll probably do, like if I'm drawing 5 cards, I can sometimes use this definition, which we'll talk about. And then sometimes I'll go, what if I found the probability of each individual event occurring and then counted the ways that those situations could be occurring in a different order, if the order doesn't have an effect on the outcome. So those things right now, it just sounds like I'm going blah, 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 but we're going to be looking at two different ways to look at most of these probability problems. And then what you have to remember if it's dependent, what does that mean?
Changes with the outcome of the first.
So whatever happened initially is going to affect what happens subsequently, right? So every time I do something like I pick a card, if I pick a card and keep it, now there's less cards. And there's less kinds of cards, right? Like if I have a king, now there's less kings. If it happens to be the king of hearts, now there's less hearts. And that choice affects the probability of the next choice. If it's a dependent situation, you can look to use combinations and permutations depending on whether or not the order matters or not. But if you're putting stuff back, or if what you do is not affected, like flipping a coin, every time I flip that coin, it doesn't affect the next outcome. If that happens, if you read the problem and you see, wait a minute, this, whatever happens initially is not going to affect what happens after that, you cannot use permutations and combinations because the whole idea of a permutation and combination is based on what?
Factorial.
A factorial. And there are no factorials when you put stuff back, right? Like how many cards could I choose on my first choice? 52, and I take that 52. But if I put it back, how many on my second choice? 52 if I put it back. And if I put it back, how many on my third choice? 52, 52, 52, 52. That's not a factorial, right? But if I don't put it back, 52, 51, 50, 49, 48, that factorial nature of it allows me the right to use a combination of permutation to simplify matters. So we're going to talk about this a lot, but don't just stare at bricks. Don't wait for somebody else to ask a question. Be constantly asking yourself, do I understand what this man is telling me? And if I don't, be brave enough to ask a question because you'll probably be somebody else's hero for asking it. All right? So make sure that you understand where we're going and don't feel bad about not getting this initially. Practice will make better. Probably not perfect, but it will definitely make better. And the more you get used to these and the more you start, you know how like when you start studying, you like to compartmentalize things. Okay, if it's this situation, I'll do this. And if it's this, I'll do this. Well, initially, it kind of feels like everything's just been shuffled up together like cards, like a big deck of cards. And your job is to try to get, okay, I got the queens over here, the kings over here, or the hearts over here, and the jack. and the spades over here. Try to get to the point where you're starting to compartmentalize these problems and go, okay, this is a dependent situation. This is a, whatever. The order does matter, and think that way, so it's going to really help you when it comes to doing these probability problems. Okay, so we talked about impossible and guaranteed yesterday. I'm just going to jump in there and start talking about some examples. Okay, so the first example I want to talk about is this, and it has a bag containing 5 red, 9 green, and 6 white marbles. So we'll just assume that these marbles are all thrown in there. They're different marbles, even though they have the same colors. And it says 3 are picked. Now, what do you think initially is the most likely marble to get if you just reached in there and grabbed one? Yeah, there's more green marbles, so it's more likely. What's the least likely to get? Red. But the fact that these marbles may look identical doesn't mean you can go, oh, well, if they all look the same, you can treat it like one. Well, that's not true, because that would mean that there would be equally likely each color to pull out when you grab one. So you have to count the actual numbers of them, okay? Now, if I were to ask you a question like, hey, 3 are picked, you're picking 3, find the probability that I get 2 red balls and 1 green one. So let's think for a second. If I stick to the definition of probability, probability says count the number of ways to get 2 reds and 1 green, and then divide, that would be the event, right? The number of ways in the event, and then divide it by just the total number of ways to pick 3. And that would be your definition of probability, or at least one way to do it. So let's think about that. If I go back, forget probability for a second, say, how many ways can I draw 2 reds and 1 green from this situation? Well, what am I drawing 2 red marbles from?
5 red marbles.
From the 5 red marbles. I cannot say, hey, there's 20 marbles. I want 2 red ones, 20C2. Because if I say 20C2, that counts the number of different ways I could pick 2 marbles. But does it guarantee that they're red? So if I want to guarantee they're red, I can only count the 2 from the 5. Does that make sense? Almost pretend like you're looking in there and going, okay, which of these red marbles could I pick? I could pick that one and that one, 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 or this one and this one, this one and this one, this one, this one. It's like you almost have an inside look at it, but the number of ways to do that would be 5C2. And I'm going to come back to this in 2 seconds. So I'm going to say 5 to choose from. I'm picking 2, and the order in which I chose them does not have an effect on the outcome. Now, after this, what do I need? So I'm picking 1 green from what?
9 green.
The 9 green marbles? So if I'm picking 1 green from these 9 green marbles, what am I going to say? 9C1, so times 9C1. Now that is the number of ways that I can draw 2 reds and 1 green from this bag. And the order in which I choose them does not have an effect on the outcome. Now, what about the denominator? How many ways can I just get 3 marbles? Doesn't matter. Because that's the experiment, drawing 3 marbles. So there are 20, right? And you're going to pick 3, and I don't care what you get, right? This could work, it could not work, it could match what I want, it could not match. 20 C3 goes in the denominator. Now, that right here is equal to this right here. But let me explain why a lot of people will miss this question on the test. A lot of people look at this, and this is what I'm talking about, memorizing the theory or learning the theory. A lot of people look at this and they go, well, if I want a red marble, and then a red marble, and then a green marble, if that's what I want, they go, what's the probability if you pick 1 marble that it's red? Pick 1 marble. What's the probability that it's red?
5 out of 20, 1/4.
So 5 out of the 20. And don't even bother simplifying. Okay? Does that make sense? Like before I even taught this lesson, if I said, hey, what's the probability of getting a king? Most of you would say, well, 1 in 13, because there's 13 kinds of cards. Or you might have said 4 in 52. If I said, what's the probability that I get a heart? Most of you would have said, oh, 1 in 4, or 13 out of 52. You knew that already, right? You might have not known this combinations junk, but you might have known that. Well, if I said, what's the probability that I get a red one? You're like, well, there's 5 red ones to choose from. There's 20 total. Well, 5 out of 20. And then I go, okay, Now you go pick another red one. What's the probability that that one's red? And you go, well, I've already picked one of the red ones, so now there's only 4 red ones left. And there's only a total of 19 left, total marbles, right? And you say 419. And then I go, all right, now what's the probability of getting a green marble? And you go, well, there's 9 greens, but now there's only 18 marbles left. So 9 out of 18. And you would have stopped right here. Red marble, green marble. Why is it bad to stop right there?
It's not right.
That's saying it's a permutation. All I have done is count, find out the probability of getting a red and a green in that order. But can't I get a red and a green by also going red, green, red, and also going green, red, red, right? So how many different ways could I get a red and a green? 3. That is equal to 3. And that number right there is me saying I had 1, 2, 3 total choices, 2 R's, 1 G. What does that feel like I'm doing?
The thing with the letters.
The thing with the letters with Mississippi. You remember when I asked you how many different unique ways could I arrange the letters in the word Mississippi? And you said 11 factorial over, or whatever it was, over 4 factorial, 2 factorial. You remember doing that? And you did the 4 factorial, 2 factorial because you had 4 I's and 4 S's and 2 P's. Y'all remember that, right? Well, this is like saying, how many ways can I arrange those 3 letters RRG? Well, there's 3 letters, 3 factorial, but because 2 of them are R's, 2 factorial. Do you really need the 1? No, but I could put that. And counting the different arrangements counts the total number of ways I could have done this, whether it's RRG or RGR or GRR. But when it's hard to count, when you're picking 10 marbles or 17 cards or things where it's impossible for you to manually think through all the different options, this is your plan. And this right here makes all of this equal to that. Now, you might look at that and go, how is that equal to this? Well, take a look. Check it out. If I really wrote this out, what is 5C2 equal to? Talk to me.
5 factorial over 3 factorial.
5 factorial, which is that number, over subtractum, 3 factorial, 2 factorial. And what does 9C1 equal to?
9 factorial.
9 factorial over
8 factorial.
subtract them, and then a 1 factorial, right? And then what is that equal to?
20 factorial.
20 factorial over
7.
subtract them, and then 3 factorial. Now watch the math on this. Right here, what does that simplify? Couldn't I cancel that? And what would that leave me with here?
5.
Does everybody see that leaves me 5 times 4 when I cancel out the 3 factorial? And then right here, what would this do? It'd leave me a 9. And what would this do? 20 times a 19 times an 18. Now you still have that other factorial on the bottom, right? Now, what do you do when you have fractions over fractions? To divide by a fraction, you do what? You multiply by the reciprocal of this. So couldn't I take that and flip it over and make it 3 factorial over 20, 19, 18? Wouldn't that be the same thing? Now look at the math. 5, 4, 9 on the top. 5, 4, 9. 20, 19, 18 on the bottom. 20, 19, 18. 3 factorial on the top. 3 factorial on the top. 2 factorial, 1 factorial on the bottom. 2 factorial, 1 factorial on the bottom. It's the same thing, but there's 2 ways to go about it. Now, what if this problem did not say how many total ways, or I'm sorry, find the probability of getting 2 reds and 1 greens. What if I'd said, find the probability of getting 2 reds and then 1 green in that order?
Leave off the 3 factorial, 2 factorial.
I would leave this off because this counted what? The number of other ways I could change the order up and still get this. But if I can't change that order up, if I have to have it in this particular order, then I wouldn't want that. Now, are these equal? Now they're not. What could I do to this?
P.
Change it to P. Because when I change this to P, what does it leave off here?
2 to 1.
The 2, which was that, the 1, which was that, and the 3 down here, which ended up being the 3 up here, which was that. So if the order is specified, you have to treat it in this order, then you can just use P's or find each individual event. If the order in which it does, when it occurs does not matter, then you can use C's like we did here, or you put that little part out front to count all the different ways that that order can happen. Are you with me? And see if y'all paying attention. If I'm putting the marbles back each and every time, what can I not do? Which means I can't use what? P's or C's. So I have no way, I cannot use this option if I am replacing them. Now what I could still do is think this way, except one thing. On my first choice, what's the probability of getting a red?
5 over 20.
On the second choice, what's the probability of getting a red?
5 over 20.
5 over 20. On my third choice, what's the probability of getting a green? 9 over 20. Nothing's changing every time, right? But did I specify it had to occur in that order? So I would still count the number of ways that I could get 2 reds and a green from those 3 letters. I would still do this. So the idea of you cannot use factorials at all is not true, because we're still going to have to rearrange, count up how many different ways that could be arranged if that was part of the problem. And if it said in that order with replacement, then you just leave that part off and stick to that. Now, those are almost everything you do in probability is going to fall into these categories. You just have to think about it. And if your brain's spinning a little bit now, totally understand. That's why I have so many review sheets, okay? To give you lots of practice to fail on a question, learn from it, and then get back on the horse. Are you with me? Okay, let's take a look at something else. How about, what if I said you're picking 5 marbles instead of whatever, you're picking 5, but I want 2 red, 2 white, and 3 green in that order. So what could I do if I said 2 red? Remember we have, hold on, 2 red, 2 white, 3 green. So back to this, we want 2 reds, 2 whites, what did I say? 3 greens? So you're picking 7 marbles. So what's the probability of getting 2 reds, 2 whites, and 3 greens if you pick 7 marbles in that order? Let's talk about both ways we could do that. Give me one more.
5, P2.
Okay, it says in that order, so you can use P's, right? Because the order has an effect on the outcome. So you're picking 2 from that, so
5 P2s.
5 P2,
6 P2.
whites, 6 P2,
9 P3.
greens, 9 P3,
And then all over 20 P3.
multiply them and all of them over 20 P what?
7.
P7. And what is that the same as? That's the same as going individually red, red, white, white, green, green, green. So what's the probability of getting a red? 5 out of 20. Now, once I pick that, what's the probability of getting the next red?
4 out of 10.
4 out of 19. Probability of getting a white?
6 out of 18.
6 out of 18. Probability of getting another white?
5 out of 7.
5 out of 17. Probability of getting the first green? 9 out of 16. The next green? 8 out of 15. Last green? 7 out of 14. And normally you'll see me write it like this. I kind of group a little bit. It's not that important, but just to kind of show the groupings. And do I put that little factorial thing out in front? Why not? Because it says do it in that order, right? If I did not say in that order, and I said, hey, We don't have to go red and red and white, white, and green, green, green to get that result. We could go green, 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 white, white, red, red. We could go green, white, red, red, white, green, green. There's all kinds of different orders. How do I count them? What would I put out front? 7 factorial over 2 factorial, 2 factorial, 3 factorial. And what could I do to this if the order didn't matter? Change it to C's.
So when you're working with those and having to put things out front, can you kind of pretend like you're arranging like letters?
I do,
Because you have to divide, yeah.
because that's what you're doing.
Right.
Your letters, your options, it's like me going, hey guys, how many different words can you arrange with it? How many different words can you make with that? Right? You would go 7 factorial over 2 factorial, 2 factorial, 3 factorial, right? I mean, that's what you would do. But that's what I'm doing here, because if I could choose them in different orders and still get the same result, still use those same letters, I would have to count each one of those orders. And that's what it does. And when you count them and you multiply them by this, that gives you your final probability. Are you seeing this? But I will want you to be able to think through all of these examples. All right, what about just jumping around? 2 cards drawn from a standard deck of cards. Find what's the probability you get an ace and a queen? So this is one way to do it. What's the probability of getting the ace?
4 out of 52.
And there you see it, 4 out of 52. Notice I will not do any simplifying. I would encourage you not to also. What's the probability once you draw an ace that you now get a queen? 4 out of 51. Now, if I had said in that order, I would be finished. But I didn't. So what do you now have to do? 2 factorial over 1 factorial, 1 factorial. Now you could also just go, wait a minute. There's only 2 ways to get it, right? Ace, queen, queen, ace, 2 times 2. That's what this ends up being. It ends up being 2. But the total 2 factorial over one of those. Y'all with me? Now what's the other way to do this using combinations? How many aces are there in the deck? 4, and you're picking how many of them? 1, so there's 4C1. How many queens are in the deck? 4, and you're picking what? 1, and there's 4C1. And how many cards are in the deck? And you're picking how many? 52C2. And even though these do not look like they're the same, they are the same. We've already shown that once, just a couple minutes ago, how they are the same. I'll probably show you again in a couple days when that memory of that washes away, just to remind you. But those are equal, and I don't care which way you do it. But I do want you to know how to do both from this standpoint. What if I ask you, what if I make up a deck of cards that has 5,000 cards, and I ask you to pick 100 of them? Do you really want to write out all 100 of these situations? But this would be really easy, wouldn't it? So being able to write stuff with combinations when it is dependent sometimes saves you a lot of trouble. Right here, about the same amount of work. But if I had to make 15 choices out of a deck of cards or 50 choices, I think I would give a problem every year where I'm like, there are 340 people in the senior class. 200 of them have dark hair, 100 of them have blonde hair, 50 of them have red hair, 10 have green hair, whatever. And I go through this situation and I say, what's the probability that if you pick 100 people that you get 60 brown hairs, 21? And I do that. And the people who can think in terms of combinations, it's really easy. But the people that go, oh, I like this way better, they've got to write out 100 fractions. And there's not a lot of room on a page for that, right? And they end up putting a lot of dots, and then they can't figure out what the last number is and end up making careless errors. So be fluent in both and you'll be in great shape. And again, if you're struggling with it now, of course, don't worry about it. You've got plenty of days. I'm feeling like our test is going to end up falling on Tuesday, not even Monday, but we're still going to hold on to Monday as long as we can.
So one question, when you're doing like, there's no specific order and
Order doesn't matter.
do you put the number of slots factorial out in front? So like you put the 2 factorial because there's 2 cards.
Because there were 2 decisions to be made, right?
Since there are 3 cards, so you put
3 factorial on top. If there are 10 cards you're picking, 10 factorial on top.
Okay.
And the only reason, and if all 10 were different, like if I said, hey, you're picking 7 cards, what's the probability of getting an ace and a queen and a jack and a 10 and a 9 and a 4 and a 2? Well, then you can just put whatever factorial on the top. You don't have to have these ones. 1 factorial is nothing. All right. I'm sorry. 1 factorial is 1. 0 factorial is 1. You don't need to put those numbers if you don't want to. I just do it a lot in my notes and in my keys to help you build consistency.
So wait, so if there are 3 slots, it would be 3 factorial over 2 factorial, 1 factorial?
No, like what if I said a probability of getting 2 aces and a queen. Well, 2 aces would be 4 out of 52, then what?
3 out of 50
3 out of 51, then what? That's the aces.
times 13 out of 50.
4
5
queens.
out of 4 out of 50.
4 out of 50, right? So there's your ace, ace, queen. But since you made three cards, 3 factorial, 2 were aces, 2 factorial, 1 was a queen, 1 factorial.
Okay.
And but over here, you could have just said 4C2, 4C1, 52C3 and be done with it. Because I picked 2 of the 4 aces, 1 of the 4 queens, and 3 of the 52 cards. But for right now, most of you are probably looking at one of these and going, I kind of like this better. Or you're going, I kind of like this better. But again, the problem with liking this better is it's really hard when you have tons of choices. The problem with liking this better is you can't do it when it's independent. You have to think this way. So you have to be versed in both. Yes, you can probably do most of the problems one of the ways or the other, but you're going to run into trouble if you're just locked in on one. And my keys don't always show both. My keys, sometimes they're older. Again, I teach 3 classes. You know how long it takes to do homework. If I redid every homework every year based on that, that's adding 2 hours to my day. I just don't have time to do it. So some of my keys are older, they're fine, but sometimes I'll do it this way and not this way. It doesn't mean that this way is wrong. It just means it's a different kind of thinking. And if you understand both, you'll understand, oh yeah, that is the same as this. And you will if you continue to examine these and think about these. Yes?
Did you bump all these assignments back in days? Because it said we're doing part 2 tonight, but we're kind of starting part 1.
I think I changed that on Schoology.
Okay.
This is right now, I'm hoping to finish up. I don't even know if we'll get to part 1. I'm hoping to finish up the probability stuff today. And then right now, it's probably looking like, we'll see, but it probably is looking like part 1, part 2, part 3 to finish off the week, review, and then, no, hold on. Today is Tuesday. 1, 2, 3. I don't know. It's probably looking like the test is going to be on Tuesday, though. So if you want to just bump everything forward, I forget what you have, but we'll get it all worked out. We'll figure it out. Okay, I mentioned this next one only because sometimes it's not just, you can't really think in terms of combinations. Like here's an example. It says 2 6-sided dice are tossed. Okay, what's the probability that the total of the 2 dice is 7? So again, in this case, I can't use combinations and permutations. Dice are not independent. I mean, they're not dependent situations. But I can use the definition of probability that says what? How many ways are in the event that I'm talking about? How many ways can I get a sum of 7? Well, let's count it. I could get a what? A 1 on the first die, a 6 on the second, or a 6 on the first die, and a 1 on the second. Or what? A 2 on the first, a 5 on the second, 5 on the first, 2 on the second, or a 3, 4, or 4, 3. Y'all with me? So how many ways was that? There's 6 ways that I could get a sum of 7. There's your numerator. Now, how many ways can I actually roll 2 die? 36, right? Fundamental counting principle. There's 6 ways I can roll the first one. There's 6 ways I can do the second one. I want to do both. 6 times 6 is 36. Number in the event is 6. Number in the whole sample space. There's a total of 36 outcomes. It's 36. And then we don't even have to simplify, but this one was not too tough. So don't always assume you're just going to use a permutation. Sometimes you just have to actually think through it a little bit. All right. What about this? In a lottery, a person chooses 6 different numbers from the numbers 1 through 40. If these numbers match the chosen numbers, then the player wins. What's the probability of a certain 6-number lottery ticket winning? Another way of saying it would be, what was the probability that Biff wins the lottery if his 6 numbers are 15, 16, 17, 28, 31, and 29? By the way, if you've ever seen a lottery ticket, you're just scratching the numbers off, right? And if you scratch the numbers off, does the sheet remember which order you scratched them? No, so you don't have to get them in the right order. You just have to have them. If you had to get them in the right order, good night. It would be really hard. I mean, can you imagine getting all 6 lottery numbers picked out of all of those millions of combinations and your last 2 are in the wrong order? You just want to punch somebody in the neck. It'd be awful. But right here, this is totally a combination. So let me ask you a question. How many ways can your 6 numbers win?
40C6.
Win.
Oh, 40C.
Win.
6.
1.
1. There's only one way. All 6 of your numbers have to be chosen for you to win. That's basically a 6C6 situation. There's 6 numbers. All 6 have to happen for you to win. There is one way you can win. Now, how many ways could you have picked 6 numbers from 40 numbers?
40C6.
And 40C6 is that. So in a lottery where there's 40 numbers, 1 through 40, and you have to pick 6, there's a 1 in 3 million chance that you're going to win, which is pretty slim, which is why most intelligent people don't play the lottery unless they're doing it solely for fun. I mean, I've got guys or friends that live in Atlanta or that grew up in Atlanta or grew up in Florida, and whenever they go back to Florida from here, they're like, oh, I always buy a lottery ticket. Just fun, whatever. Well, I play poker with my friends too. It's fun, but I don't do it to pay the power bill, right? I don't do it when I get low on cash and I'm like, man, I'm feeling it. If I can just hit it, then I'll be in great shape forever. That is foolish. That's throwing your money away because the chances of you winning are slim to none. Now, every now and then these Powerballs get really big, just massive. And people start doing the math on it. They're like, wait a minute. The payout's $38 million. And I've got a 1 in 3 million chance. Why don't I just buy all 3.8 million tickets? Every possible combination, I'll buy it up. And there are people that do this. They try to buy every single possible combination, and they can do it. But the problem with that is when people start doing that, more people are buying tickets. Sometimes you end up with a 15-way tie. So even though the chances of you winning are certain, right, you end up having to split that money with 10 other people. And you end up still losing money. Sometimes you get lucky. I mean, there are people that have won massive lotteries, and they're the only, and zillions of people are buying tickets. Like there was one that recently, well over 100 million, and people were coming from out of state, having their relatives buy them up tickets just for, you know what, you never know, right? But in that situation, there are way more tickets that are bought, and a lot of times you get multiple winners. When you get multiple winners, they're all splitting that pot up, you know? So anyway, I would argue that the lottery is a terrible idea unless it is solely for fun. If you're like, and you know, you can win smaller amounts. Like you don't have to match all 6 to win. That's like the major pot. You can hit 4 of the 6 or 3 of the 6 sometimes and win $10 or $20, a couple $100. Have you seen the movie? It's the Christmas movie. Is it not Family Guy?
That's a great Christmas movie, though.
Yeah. What's the movie with Nicolas Cage and Tia Leone? You know what I'm talking about? And Cheadle, Don Cheadle?
Christmas Vacation.
No.
Oh my God.
Family Man. Y'all have never seen this? Oh, it's phenomenal. You got to put it on your Christmas list. I watch it every Christmas.
It's a Christmas movie?
Well, it takes place during Christmas, and there's a lot of Christmas scenes around it. You know, Christmas parties.
Die
and-
Hard. Everyone calls it Die Hard.
Yes.
Yeah.
And I don't have that on my list, but I do like that movie. But anyway, the point is, it's a great movie, but there's a scene in it where this guy, Don Cheadle, walks in. He's an Academy Award winner. Whatever. Anyway, he walks in there, and he's like, man, I got this home money, man. Pay me up. He walks into like a convenience store with this $200 ticket, and the guy thinks he's a fraud and whatever, and it starts this exchange. Guns were pulled, whatever. But anyway, it's a great movie if you want to see it. It's fun. It's not like raunchy. If you want to keep it clean, it's awesome. You can watch it with the kids one day.
I like how you just said guns were pulled, and you're like, you can watch it with little kids.
You can, because it was like a really minor scene. It didn't escalate. Nicolas Cage
Yeah.
calmed the situation, whatever. It ended up being very interesting. It's really a good movie. Take my word for it. It's not like you're an old dude, man. I mean, it's not Step Brothers. I mean, but whatever. It is a good little Christmas movie to watch. Anyway, bottom line, probability of winning pretty slim, and sometimes the lotteries go 1 through 60. So 1 through 60, you got a 60 C6, which is so much more difficult to get. All right, let me talk about mutually exclusive. Mutually exclusive events are different from events that are not mutually exclusive. Like, for instance, what if I said, what's the probability of getting a queen? You would say 4 out of the 52 are queens, right? What if I said, what's the probability of getting a queen or a king? You would say, well, the probability of getting a king is 4 out of 52. Queen is 4 out of 52. So the probability of getting a king or a queen would be 8 out of 52, right? And it appears like we just added the two individual probabilities. But there are no king of queens, are there? I mean, there's a TV show that's the king of queens. But you can't get the king of queens. What if I asked you, what's the probability of getting a king and the probability of getting a heart? The probability of getting a king is 4 out of 52, right? And the probability of getting a heart is what? 13 out of 52, or 1 out of 4. But if I do that, what if I just double counted? The king of hearts, I counted in both groups. This is the situation where, like, if you think about a Venn diagram, there's overlap, right? Kings and queens, totally separate. Find the probability of one, probability of the other, add them together. But if there's an overlap, like the king of hearts, you can't double count it. So what do you end up having to do with a probability situation like that? Subtract the probability of the overlap. So if things are completely mutually exclusive, which means one has nothing in common with the other, kings and queens, nothing in common, I can add the probability of A union with B, or the probability of getting this or this is that. Okay? But if I say if they're not mutually exclusive, which means there's overlap, then you can go ahead and still find the probability of both, right? 4 out of 52, 13 out of 52. But since there's that one problem that overlapped, there's a 1 in 52 chance that you get the king of hearts. Subtract that probability from it. And you're not going to see a ton of that, but just be careful about situations like that. It's very easy to forget that, oh yeah, I counted that twice. You don't want to count it twice. You want to get rid of what you overcounted. Yes?
Can the people at AB site go get lunch, so we have time to eat before lunch?
You can do whatever you want. All right.
I'm sorry, Sam.
Okay, here's an example of this. Do y'all know what a face card is, by the way?
Yes.
A lot of people think face cards are like tens, jacks, queens, kings, and aces. A lot of people think face cards are even more, because they show up in a royal flush. Right? It's royalty, it's a face card. And then a lot of people think ace is a face card. What's a face card?
Jack.
Has a face. The only ones that have faces are what? Jacks, queens, and kings. Okay? Now, you might have parents that call aces face cards, whatever, but if it's got a face, it's a face card. Okay? So, how many face cards are in a deck?
12.
3 kinds of face cards, but there's 12 cards, right? 4 jacks, 4 queens, 4 kings. So, the question said, one card is selected. What's the probability that the card is a heart or a face card? Am I okay with just find the probability that I get a heart and find the probability that I get a face card and adding those two together? Why is that? Because they are not mutually exclusive. They include a common situation, which is what? The jack, the queen, and the king of hearts. So the probability of the overlap is what? 3 out of 52. So if you want to go ahead and just add those two up, the 13 and the 12 out of 52, that's fine. But don't forget to subtract off where they overlapped. And they overlapped in 3 situations out of those 52. And that's what I'm talking about when I'm talking about this mutually exclusive stuff. And it can be much harder than that or more difficult than that. But that's a basic example. All right, so probability part 1 is going to be your homework tonight. This is kind of how we're going to work. And we've got a few more minutes, so I might just kind of pop around. We're going to talk about odds real quickly before the bell rings. But probability part 1, I want you to go through it and just do the best you can. And the way we're going to do this over the next few days is when you come in the next day, you come in with questions about part 1. And then the next day, we're going to do part 2. And you're going to come in with questions about part 2. And we're going to do that. And if we do that, we're going to finish up with part 3 on Thursday. And then we're going to review Friday, probably Monday, test on Tuesday. All right? Okay, so one thing about odds I want to talk about. A lot of people don't know that odds and probability are different because the world uses them like, oh man, what are the odds? And they say that the same way as they say, oh, what's the probability? Or what are the chances? But odds are not probability, okay? Odds are defined differently. Probability is defined as this. The probability of success would be the number of ways to achieve that success divided by the number of ways to either succeed or failure. So basically, the number of ways to get what you're trying to get over just the total number of ways of getting it or not getting it, whatever, just the total number of ways. So like if I said, what's the probability of getting a 1 if I roll a die? Well, there's one way to get a 1, but there's 6 ways to get numbers on a die, right? 1 and 6. Now, that's not what odds does. Odds defines success as this. The number of ways to get success, not over the total, over the number of failures. But they don't put it over very much anymore. In old textbooks they did. They use a colon. So instead of like the odds of getting a 1 would not be on a roll of die, is not 1 out of 6. It's what?
1 to 5.
1 to 5. 1:5. Are y'all with me? Not 1 out of 6. Now, what if I said the odds that it's an even die? I mean, if it's even, what is it?
1 to 1.
3 to 3, which you could reduce that to 1 to 1. Are you with me on that? If I said, what's the probability of getting a king? What do you say? Or 4 out of 52. I'm never going to simplify. 4 out of 52. What are the odds of getting a king? 4 out of 48, because there's 48 non-kings, right? So make sure you understand odds and probability. Now, I'm going to mess with you a little bit because I'm going to do stuff like this. Jump down to number 9. Or jump down to number 5. If these are the odds of an event occurring, so this right here would be the odds, we'll say, of success. Odds of success, 3 to 4. What is the probability of success? Do y'all see what he just said? He said 3 out of 7. Do y'all see that? Because odds says first number would be success, second's failure. Probability says numerator is success, but denominator is what? All of it, success and failure. 3 plus 4. Are y'all with me on that? Jump back up to the number 3. This says state the number 3. This says state the odds that something occurs if this is the probability. So if this is the probability of success, what would be the odds of success? What do these numbers represent? What does the 7 represent? Success. What does the 15 represent? Success and failure. What can you conclude about failure then?
8.
It must be 8. Now, what's the odds of success then? 7 to 8. And be careful because sometimes I'll mess with you. Like look at these number 9. Number 9. If the odds are 6 to 1 against it occurring, what's the probability that it will? So this is like saying the odds of what? Failure are 6 to 1. What is the probability of success? Check it out. So that is your F. F, whatever that letter is, that comes first, right? And then this would be your success. But success would have 1 on the top and 1 on the bottom. Both. So just remember, if I say odds of F, the first is the F, the second is the S. If I say odds of S, the first is the S, the second is the F. If I say probability of success, the top is the S, the bottom is both. If I say probability of failure, the top is the F, the bottom is always both. Are y'all with me on that? But this top number always goes with that letter, and this first number always goes with that letter. And then I'm going to let you, we've played enough with probability that you have a shot of doing these. If you butcher them, don't worry about it, but do not do this. Don't just pull up the key and copy crap down. You're not knowing it. Just ask me questions tomorrow, and we'll answer all day long. That literally is how I've designed this. It's for you to figure out what you know and don't know, and every day ask questions about it until I beat it so mercilessly into your skull that you remember. All right? All right.